Hello everyone, welcome to our first Birmingham Institute of Physics evening lecture of this academic year. Obviously things are looking a little bit different to normal, so thanks so much for joining us online this evening. It's a shame we can't be welcoming you to campus as normal, but hopefully you'll enjoy this evening in a new format and maybe reach some people that wouldn't have been able to join us on campus anyway. So my name is Kat Grover. I'm hosting and representing the University of Birmingham this evening. My job is the admissions manager in the school, so I have to give a quick plug for any of you who are thinking about studying physics with us in the future. We know this year's been a little bit difficult for picking universities, so if you do need any advice and you want to get in touch with us, just search for the admissions office in physics at Birmingham and I'd be happy to chat to you as well. So just a bit about the technicalities of this evening. If you do have any issues or you can't hear us or you can't see the screen or something like that, please just let us know straight away. It's the first time we're using this new platform, so hopefully it will all run smoothly, but don't be afraid to speak out. To do that, there should be a little arrow in the top of your screen, and then you should be able to click on that and to type a question to ask us. You won't be able to turn your camera on or use your microphone today, so it's all just typed questions. And of course, we welcome questions to the speaker. You can type those throughout the talk as they come to your mind, and then at the end of the talk, I will read them out and ask our speaker the questions. I don't need to read out your name or anything like that, so feel free to ask anything that you want. So just to plug the rest of our series this term, we've publicised the rest of the lectures up until the end of this term, so up until Christmas, every 3 weeks from now. So that's the 17th of November and the 8th of December. So these are the two talks that are coming up. So we've got one on topology on the 17th of November from Chris Hooley. And on the 8th of December, David Garosa will talk to us about gravitational waves. So to register for those, you just need to do the same process as you registered for these lectures. So I'm just going to stop sharing my screen now as the speaker sets up, so bear with me. Okay, so our speaker tonight is Professor Victor Debattista from the University of Central Lancashire. He leads the Galaxy Dynamics group there, and this studies the formation and evolution of galaxies using state-of-the-art supercomputer simulations and modelling techniques. He's going to speak to us this evening on the work he is doing using the European Space Agency Gaia space mission to understand our home galaxy, the Milky Way. So thank you so much for joining us, Victor, and over to you.
Thank you. Okay. Okay, so I hope you can all see my screen now. With that out of the way. Okay, so yes, thank you. I'm very happy to be giving this first lecture of the series for the IOP. My name is Victor. I'm at the University of Central Lancashire, and I'm in the Jeremiah Horrocks Institute. I'll tell you a little bit about us first. Okay, Jeremiah Horrocks. Who was Jeremiah Horrocks? He's not very well known. He died young, unfortunately. Jeremiah Horrocks predicted that there was going to be a transit of Venus. That's when Venus passes in front of the sun, obscuring a little bit of the light. That's what you're seeing over there. This is an artist's representation of what that was like. This was in 1639. That was about 50 years before Newton came up with Principia, before gravity, before mechanics as we understand it today. And that happened, the observation happened about 6 kilometers away from the university. So that's why we've chosen him as the name of our institute. And our logo harks back to this. It's again an artist's representation, the sun with Venus passing in front of it. That's a really big Venus, of course. The real Venus is much smaller than that. But we use this technique nowadays, besides anything else, to find planets around other stars. Some of my colleagues at the university do that type of work. I don't work on that myself. The reason why I'm bringing Jeremiah Horrocks, apart from the fact that we are part of we're named after Jeremiah Horrocks, is to make a little bit of connection with what he did. What he did was what we call celestial mechanics, which is the study of the motion of objects in space. He was studying the motion of planets in the solar system. I'm studying the motions of stars within the Milky Way. So very related. Of course, there's been a lot of work in the meantime. If nothing else, we have Newtonian gravity and then Einstein gravity. So we understand gravity a lot better than, well, they didn't really have a proper concept of gravity in the day. But yeah, there's a little bit of an affinity between what he does, what he did, and what I'm doing. I'm working on the formation of galaxies, and at the moment, my focus is a lot on the Milky Way. So the story that we're going to be telling about how galaxies form and evolve starts off here, right? You've probably seen this before. This is the cosmic microwave background. This is the leftover heat from the Big Bang. We're seeing the universe as it was about at an age of about 300,000 years. The universe formed in this big explosion, and we're seeing the leftover heat as it's now cooled down to a temperature of about 2.7 degrees Kelvin, 2.7 above absolute zero. And what you can immediately see when you look at this is there's these little ripples all over the place. We can measure the scale of those ripples, and that tells us, that gives us a lot of information about what the universe is comprised of. You see, you have this, there's a lot of ripples on a scale of about 1 degree. And then there's smaller and smaller scales at which we see stuff. And that tells us what the universe is comprised of. And this is the answer of what it's comprised of. It's 5% are the atoms that we're familiar with, the ordinary stuff we're familiar with. Then about a quarter is dark matter. We don't know in detail what dark matter is, but it's in some ways not very surprising that what type of material it will be. It will be some kind of particle physics, something like, let's say, you remember a few years ago, we discovered the Higgs boson. The Higgs boson had been predicted for decades, and then after decades, we finally found it. Dark matter is probably something very similar. We will eventually find it. There's many possibilities about what type of particle it could be, but it hasn't been found directly yet. But the really mysterious part is not the dark matter. The really mysterious part is this dark energy. It's about 3/4 of the universe. We don't know very much about it. It acts nowadays a little bit like anti-gravity. It's pushing the expansion of the universe faster and faster. But really, there's very little solid evidence of what it is. We don't really know. And there are now experiments and space missions being designed that will start to give us a better handle on this. When we discover the dark matter particle, I'm sure that will be a Nobel Prize. And when we get better constraints on what dark energy is, that will be another Nobel Prize some point in the future. When that will be to be determined, but watch the space. But anyway, the part we're interested in here is the part that we see the stars. Stars are made of, well, atoms, and not necessarily atoms. It could be, you strip out the electrons, so you get plasma. That's ordinary matter over there. And that's what most of what we see is. This is an example of a simulation called the Illustrious simulation that was run by a big consortium where you're seeing how galaxies form. And what you're seeing are these filaments of dark matter, where these filaments intersect. You get condensations of gas settling in there and forming stars eventually when the density of the gas gets high enough. And that's how galaxies are born. And I've highlighted a few of these over here. And when the galaxies are born, one of the things they do is some of the stars explode and blow out the gas. So what you're really seeing in this picture is, in this particular simulation, this is not the real universe, this is a simulation of the universe, you get this hot gas surrounding where galaxy formation is taking place. And like I said, the hot gas is only about 5% of the universe. So really this image should emphasize the dark matter more, but just simply because the authors were interested in understanding where the gas is, they've highlighted the gas more. A slightly better representation might be this one, which came out just recently. It was on Astronomy Picture of the Day, if you follow that, where you can really see the filamentary structure of the dark matter and galaxy clusters and galaxies forming at these intersections. And the puzzle is to try to understand how these galaxies form. So that's what I'll be telling you about. So if we go back actually one step, these regions are surrounded. So where you see stars, they're surrounded by what we call a dark matter halo. This one's particularly clear here, for instance. You can see a large dark matter halo around this galaxy. So that's an example of a dark matter halo. It has many satellites within it. And then at the very center, what would happen is the gas would cool down and settle to that central region. It would pool in that area. It would be rotationally supported, so it's spinning. And then the density gets high enough and you start forming stars. And you get spiral galaxies like this. This is an example of a typical spiral galaxy. That's when we view the galaxy in what's known as a face-on view. We're seeing it sort of from above. I might use this term later. That's face-on. If we look from this side, if we sort of look from this direction, we would get a view like this. This is an edge-on view of a galaxy. You see it's pretty thin. You have a distinct sense that things are rotating clockwise over here. And that is more or less what most galaxies do. Not all galaxies do that, but that's what most galaxies do. You might notice it's red in the center, blue further out. It's red in the center because these stars are old. The stars further out are younger, typically, and so they tend to be bluer. Young stars include lots of very massive, very hot stars, so they shine in the blue light. Right. So we have had for almost 100 years now Edwin Hubble's classification for galaxies, and it looks like a tuning fork. We call this the tuning fork diagram. You might have seen this before. We refer to these galaxies as elliptical galaxies. These are more or less balls of stars that are moving relatively at random with respect to each other. I won't have anything to say about these. Then there's the spiral galaxies, like this one over here, that we're sort of familiar with, even just from cultural representations of them. And then there is the lower branch of the tuning fork, and this is the barred galaxies. And we call them barred galaxies because there's a bar going right down the center. And so the classification scheme is capital S, that tells us it's a spiral galaxy, capital B, that tells us there's a bar, and then A, B, C tells you how big the bulge is, amongst other things. The Milky Way is a barred galaxy, it's one of these, and it's sitting sort of intermediate between these two. So it would be capital S, capital B, and then little b, little c. That's the Hubble type of the Milky Way. And here's an example of a real barred galaxy. We see sort of a central bulge region. There's the bar over there. You can see this region is relatively reddish. The stars in this region tend to be old, and the same is true in the Milky Way. And trying to understand the age distribution in there is one of the things I'll talk a little bit about. And then further out in the disk, we start seeing younger stars. So again, blue, you see strong spirals, and there will be stars all over the place there. And these pinkish regions, that's where star formation is taking place. So this is sort of a quintessential barred galaxy, nothing very special about it. The Milky Way is also a quintessential barred galaxy, nothing special about it. So one of the things we're doing when we study the Milky Way is we're not just studying the Milky Way, but we're studying how galaxies in general form. It turns out that the barred galaxies are very common. Amongst the spiral galaxies, the spirals and the barred spiral galaxies, roughly 2/3 of galaxies have a bar in them. Right, okay, so we carry on. This is a view of the Milky Way that we will never have. This is just an artist's impression. This is, you're seeing just the stars, of course. Well, the stars and a little bit of the gas. So again, just the 5% over there. We see the bar as we think it is in the Milky Way. You see this region is relatively old. I can say that now. It's red, so this is old. And this region has younger stars. That's why it's blue. And there's star formation regions dotted all over the place, these pinkish regions. Remember, this is an artist's impression. This is not what we actually see. The sun would be sitting somewhere over here, okay? What we actually do see is this. If we look at the sky, for instance, in the Canary Islands, we see this bright band of light, which we call the Milky Way. And the name comes from the appearance on the sky. Now that's very interesting. There's a band of light over there. Here's another band of light. which is the zodiacal light. And in a really dark site, you can see this directly. And you can see that Venus happens to be passing through this region. The fact that this is a band of light and that it's associated with the zodiac tells us two things. First of all, what this represents, the fact that there's light. We're seeing the reflected light of the sun. Nothing in the solar system emits light directly. So any light we see has to be reflected back to us from the sun. And we're basically seeing lots of little bits of dust in the plane of the solar system that is reflecting the light that falls on it, reflecting the light of the sun back to us. Now, the fact that this is a band of light means that it must be a flattened structure, a disk. We know this, you're sort of familiar with pictures of the solar system, and we've traveled around in the solar system now. We know that it's a flattened structure and that we are within it. The same is true in the Milky Way. The Milky Way is a flattened structure and we are within it. And that's how we start to understand our place in the universe and our place in this galaxy. If we look at this more in depth, we would see something like this. You can see that it's a flattened structure. There's also lots and lots of dust. Stars are actually extremely polluting. They produce a lot of dust. And there's also regions of star formation, which are these pink regions that you see over here. Okay, so that's sort of the optical view, the visible light view of the Milky Way. And I said there's all this dust that gets in the way. It inhibits us seeing things clearly. If we look at in the near infrared instead of in the invisible light, we can, the effect of dust is lower. We can see more of the Milky Way. And the Milky Way looks like this. There's a central, what we call bulge region, and then there's a disk that goes further out. And we would be sitting some distance out in the disk itself. You can see that there's still the effects of dust, but it's not as extreme as in this image over there, but we can't see much of anything behind it. Right, so just so that you're familiar with the terminology when I start talking about things, just very briefly, what the Milky Way is comprised of. There's a central bulge of stars. This is the old stars. The bulge is part of the bar in the Milky Way. And then we're seeing this galaxy, this cartoon of a galaxy from the side. So edge on. This is the disk in here, and the spirals would all be in that general region. And the solar system is somewhere out here in the outskirts. We're not sitting at the center of the galaxy. There is also another structure called the halo. The halo is comprised, the stellar halo is comprised of stars that were initially in dwarf galaxies that the Milky Way cannibalized and now have been stripped out and just formed a sort of spherical distribution, roughly spherical distribution of stars. In the Milky Way, that's about 1% of the total mass, so it's not a very important contribution to the overall mass. So I don't work very much on this. I won't have very much to say about the halo. I will tell you a little bit about the bulge, the disk, and the outer parts of the disk. So before we actually start doing some interesting science, we need to ask, how do we study the Milky Way? And the Milky Way presents us with two problems, two very important problems. One is that space is big. And what that means is that determining distance is extremely hard. And let me show you what I mean by that. Suppose there is this star over here and we want to determine the distance from it. The way we could do that is the way we can tell the distance of an object relative to us on Earth. We have two eyes, we have two images of something, and our brain interprets that because we have two images, it interprets the distances of objects. If you try determining the distance of an object with one eye closed, it gets much harder because you've only got one image. I don't suggest you try that right now. It might be a little bit dangerous in front of a computer. Okay, so suppose we have the star. We observe it in January against the background of very distant stars. The star would then appear to be on this side. So we would see the star there. 6 months later, when the Earth has gone halfway around the sun, we have this image of the star, and now it projects over there. And so the star has moved to this location. So if we can measure how much it changes by over the course of a year, we can measure how far away the star is, just very pure, simple algebra that the ancient Greeks could have done for us. Turns out, though, that the distances are so large that these angles, this angle P, the stellar parallax, is very hard to determine. And let me tell you what I mean by it's very small. So you've seen the full moon. You can probably see the moon outside right now. The moon covers about half a degree on the sky on average. Okay. Now, if you hold a pinky at arm's length, that covers about 1 degree. 1 degree can be divided into 60 what we call arc minutes. And each one of those arc minutes, we can then divide into 60 further arc seconds. So in 1 degree, there are 3,600 arc seconds. So you can imagine how tiny that is. Okay, it's a very tiny angle. The nearest star, Proxima Centauri, has a parallax, this angle over here, of about 0.77 arc second. And that's just at about the limit of what we would be able to observe from the ground. We can maybe go half that from the ground that we'd be able to see, but it starts getting difficult. But Proxima Centauri is extremely close to us. If we wanted to study, for example, the Orion Nebula, which is the nearest large star-forming region, that is at a distance such that its parallax, how much it changes across the background in the space of half a year, is 0.0024 arc seconds. What is that angle? That's about like trying to make out a van on the moon. You can imagine that's extremely hard to do. Seeing with the naked eye a van on the moon, or even with a telescope a van on the moon. Now, the Orion Nebula is not far. The Orion Nebula is actually quite nearby. And so this is part of the problem, that most objects are very distant from us, and then it becomes very hard to tell what the proper distance is. And the fundamental problem is these angles are very tiny. And that's where the Gaia satellite comes in. What the Gaia satellite is doing is it's measuring these very, very small angles. It's doing it from space. It measures parallaxes to an accuracy that's given there. And to get a sense of what that's like, it's what it says over there. That's like being able to resolve an apple on the moon. It's a remarkable telescope. It's produced 2 data releases so far. We're in the 2nd data release. And next year, maybe the year after, COVID permitting now, there will be a 3rd data release. And it's already given us positions of about 1 billion stars, some better than others, of course. The first data release only included about 1.5 years worth of data. The next data release is going to give us much more data. And this allows us to start pinning down things very accurately. And then when we combine it with ground-based observations, we can really start learning a lot about the Milky Way. So that is one way in which we're solving a problem. Incidentally, the Gaia telescope itself is quite tiny. This is the footprint of the Gaia telescope. And if you compare it with the Hubble Space Telescope, for example, that is not a very big telescope. Its advantage is that it's up out in space and it's observing the entire sky repeatedly. The largest telescopes in operation now would probably be the very large telescopes. In Chile, there is the extremely large telescope being built that should be coming online in a couple of years. And there's also this 30-meter telescope that's coming online. The follow-up to the Hubble Space Telescope is this James Webb Space Telescope. You can see most of these are larger than the Gaia telescope itself. And then to show you that astronomers are not always very creative, this is the extremely large telescope, and there was this plan, this thing in the background in white that has now been canceled, but originally was called the overwhelmingly large telescope. Well, yeah. We're only talking about this little bit of light collecting power when we're talking about the Gaia satellite. Now, the second problem is not only is space big, but time is also big. Or said another way, things change very slowly. So I'm going to show you 2 slides, and they're very similar. So please pay attention to what's going to happen when I hit my space bar here and we go to the next slide. let's do this experiment. Let's suppose we were very, very patient and we waited 1,000,000 years. How would this change? In 1,000,000 years, this is what happens. I hope that's appeared by now. What you should have seen is a very, very tiny rotation. The bar has rotated by roughly 1.5 degrees in 1,000,000 years. Now, of course, we don't have the patience of nothing else to wait 1,000,000 years. So clearly, we can't do science that way. We can't do our study of the Milky Way this way by waiting this long. So what we do instead is we speed it all up by putting it on a supercomputer. And that's the kind of work I do. We create big models of the Milky Way. We have a supercomputer at the university, and then there's a national facility that we also use, plus supercomputers that our collaborators work on. And we produce models of the Milky Way. And then once you produce those models of the Milky Way, you have to compare them with the real data and understand what is going on. So what is it that you need if you want to simulate galaxy formation? There's a bunch of things that are necessary. I told you at the start that there's dark matter. We need to track the dark matter, and we need to track the gas. Initially, that's mostly hydrogen and helium, because that's what the Big Bang produces. The gas needs to be able to cool. It needs to be able to turn into stars. Once those stars form, they need to be able to explode as supernovae. The supernovae heat the gas. They inject energy into the gas. And they also inject into the gas heavy elements. I'll be talking about these a little bit more later. There's two types of elements we're particularly interested in: iron and oxygen or magnesium. These are the sorts of things we refer to as alpha elements. I'll explain why later. And of course, as we're doing all of that, we need to keep track of gravity, how things are moving relative to each other, how the gas is moving, how the dark matter is moving, etc. And we're part of a collaboration that has been developing codes to do this sort of work. Historical one is gasoline. This is now slowly being phased out, and we're moving to a new code called Chunga. These codes, especially Chunga, is publicly available. So if you have a supercomputer sitting around, you're welcome to try your hand at it. And you basically produce models and run models and then start comparing them with the Milky Way. So let me show you one. This is one of our simulations. It's one that we've used to study the Milky Way, because it has a bar, and I'll be showing you some results from the simulation. I won't be able to show you movies. One of the fun things about the type of work I do is that we produce movies because of bandwidth considerations. I can't show you movies here, but if you want to start looking at some of these things, I'm going to be putting some links at the bottom. You can look at those later. So we developed this software for looking at simulations. My collaborator developed this software for looking at simulations at different wavelengths. So you have sliders here to look at the galaxy from different orientations. You can look at it at different wavelengths, in the red light, in the blue light, and the infrared, the ultraviolet. And you can also see we have just two simulations set up, but one is a barred galaxy and the other one is a non-barred galaxy. So you're welcome to go off and try that later. Right, so this is the type of simulation that we end up with. A barred galaxy with spirals in it, sort of like the Milky Way. So I'm immediately going to start telling you some science that we've been doing in my group. I'm going to start by looking at the bulge of the Milky Way. Actually, let's not look at the bulge of the Milky Way. Let's start by looking at the bulge of this galaxy, ESO 597 G036. Why am I showing you this? Well, you can see, I think by eye, it's an edge-on galaxy. We're seeing it from the side, and we can see clearly this sort of peanut shape. We sometimes refer to this as a box shape, although this is much more this is closer to a peanut shape. Sometimes we call it an X shape because you can also see an X in there if you want to. And that is a type of bulge that is extremely common in the universe. Why am I showing you this? Because the Milky Way has a bulge that looks like this, except that we don't see it quite like that. And I'll show you what I mean by that in a moment. Right, so that's peanut-shaped bulges. You're now familiar with what they look like. This is the Milky Way. Again, I showed you this image before, but now I've added something for you. I've drawn two horizontal lines. Those two horizontal lines are there to guide your eyes a little bit. You will notice that if you look on the left-hand side and you compare that with the right-hand side, The left-hand side looks like it's a little bit more vertically extended. It's a little bit thicker. What's going on? Why is the bulge of the Milky Way thicker on one side than the other? What's happening there is that in the Milky Way, there's a bar, and the bulge is part of the bar. The bar is not quite pointing at us, but it's close to pointing towards us. This is the near side of the bar. This is the near side of the bulge, not the bar. This is the far side of the bulge. And because it is nearer on the sky, this appears larger than this side. So just there, I gave you evidence that the Milky Way has a bar. And this was indeed part of how we discovered that the Milky Way had a bar. People had been saying so for decades until we got this image. It was again another space mission. It was called COBE. It showed us this, and immediately it was obvious. Oh yes, the Milky Way needs to have a bar. And so what we're seeing, the bulge is just part of the bar. The bar is not just the bulge. The bar goes a little bit further out. But we're seeing the vertically extended part of the bar. That's what our bulge is. So great. The Milky Way, remember I told you, is SBBC, and this is the B part, the capital B part of the classification of the Milky Way. Now, if we look at our simulations, we also form these. This is the same one as I showed you before on that web page. You see it has one of these X-shaped bulges, except that we don't see the bulge like this. In this case, what we're seeing is this is as though the bar, rather than approximately pointing towards us, is on the plane of the screen as you're seeing it. We don't see the Milky Way like that. We don't see the bulge of the Milky Way like that. This is how the dinosaurs saw the Milky Way. In the meantime, you know, that 1 degree over 6 million years has added up, and the galaxy has now rotated to only about 27 degrees away from our line of sight. And it looks more to us like this. So if you squint, you maybe can see that there's a little bit of an X there, but it's not that clear. But nonetheless, that's what we have. That's the view we have, and we have to live with it. So we can try to understand what's going on based on the view we have. Oh, another, if you want to see a movie this time, this was a movie that we released. We had a press release and we released a movie with it. And this managed to find its way on Wikipedia. So it's readily accessible. Just go to Wikipedia, enter Galactic Center, and you get, you know, an animation of what an X-shaped bulge would look like if you could fly all the way around it. Right. But carrying on, we think we understand how these things form, and they're intimately related to the presence of a bar. The bar can do two things, and these are simulations that you're seeing here. On this side, the bar is bending. You see it does this funny U shape, bending in the opposite direction there. And at the end of that process, you end up with something like this, one of these peanut bulges. The other thing that the bar can do is it can grow, and as it grows, it captures stars and it captures them onto orbits that produce this sort of structure. So we have two mechanisms. We don't know which is the correct one for the Milky Way. It's something that people are actively interested in, something that I'm very interested in trying to find out, but we don't know the answer to that yet. Nonetheless, at the end of these processes, you end up with a structure like this. Now, I'm going to tell you about a couple of puzzles that come from how we observe the bulge of the Milky Way. So, if this is the bulge of the Milky Way, we're roughly observing it from here. Not quite, about 27 degrees away, I said. But anyway, we look more or less along this direction. And as we reach the bulge, we get a high density of stars over there, a lower density of stars over here. And then as we hit the far arm, we get another high density of stars. And indeed, when we go in the Milky Way, we find a high density of stars there, corresponding to this point. And then a dip in between, that corresponds to roughly this region. And then on the far side, when we hit that point, we get another bunch of stars, another peak in the stars. So this is just the brightness as we observe it, but the brightness as we observe it is related to how far away the stars are from us. Now I've pulled a little bit of a fast one there. I'm telling you that we're seeing those two arms of the bar. That's true if we look at stars that are metal rich. So I have to start by explaining what I mean by metal rich. When we talk about metallicity in astronomy, what we mean is the amount of iron typically as a proportion to hydrogen, and then we measure that relative to the sun. So the sun has 0 metallicity. It doesn't mean it doesn't have iron. It has iron, but relative to the sun, it has 0 because it's the same as the sun, of course. A star here with metallicity of -1 has about 10% as much iron as the sun. And this would be a star at 0.5, you would have about 3 times as much iron as the sun. So the the metal-rich stars have this double peak in the density. So they have a very pronounced peanut shape. When we look at the metal-poor stars, stars that have anywhere from 1/3 to 1/10 as much iron as the sun, what we get instead is this distribution over here, and there's only a single peak. Now, an important point to realize here is that these elements, iron, there's very little actual iron in the star, so it doesn't really affect the gravity of the star. It's a very small, minute quantity. So why should the stars that have little iron behave very differently from the stars that have a lot of iron? That's a puzzle. They're both in the same Milky Way. Why should the Milky Way distinguish one from the other? So that was one of the puzzles we started with that we were trying to understand. And, this was back in 2012 that these observations were made, and this result was discovered. Right, so that's one puzzle. And another puzzle that arises is, this is a little bit more complicated to explain. This is the sun. Imagine this is the sun over here, and at the center of the galaxy, there is this bar. And if we look along a particular direction, we can measure the average distance of stars, and then we join a line to the average distance of stars, and we can measure an angle alpha. Okay, this angle, this is the Greek letter corresponding to A, alpha. Now, what is interesting is that we can measure this for stars that are young, and we can measure that for stars that are old. So here is that example. When alpha is small, we have a very elongated bar because the value there is very different from the value there, and everything is twisted towards us. When the elongation is almost perpendicular, we're thinking of having something that is rounder. So over here, we would be seeing a structure that is not quite as strongly elongated as this bar, as shown in this cartoon. So the other thing we can do, like I said, is measure the age of stars. There's a particular type of stars which we call Miras. These are variable stars, and their period tells us something about their ages. So the ones that, the youngest stars, young stars here, by the way, this is 3 billion years old, yeah? Astronomical numbers get large quickly. That's why we call them astronomical. This is 3 billion years old, so relatively young. They will have a variation that is longer than stars that are older. Older stars pulsate faster. And what you see when Catchpole et al. Back in 2016 did these observations for the Milky Way, that the young stars have a very elongated bar, and it gets increasingly round as you look to older and older stars. That's basically the point I was getting at. Stars of different chemistry and stars of different ages in the center of the Milky Way, in the bulge and in the bar, are doing different things. So those are a couple of puzzles. They're in the same galaxy. Why on earth would they do such things? Why on earth would that happen? And so that's the problem we set out to solve. And I'm going to show you what happens in our simulations when we try to do this. And this is only a couple of years old now. So we start off with a galaxy like this. We're seeing it from the side. Everything is nice and happy and mixed together. And then we split up the stars in there into 5 groups. Those that initially have orbits that are nearly circular, perfectly circular would be here. And those that have more elongated elliptical orbits. Okay, this is the initial orbits. And then we run a simulation, the term we use, and a bar forms, and then we study what happens to these different populations, these different groups. So the ones that had nearly circular orbits, if we look at them face on from above, we see a very strong bar, okay, very elongated. Whereas if we look at the ones that had more elliptical orbits, curiously, they form a more rounded bar, less strong bar than this one over here is. That's when we look at the galaxy from above, face on. If we look at the galaxy from the side, the ones that had the more nearly circular orbits remain quite thin, whereas those that had the elliptical orbits have fattened up considerably in the vertical direction. They've thickened, they've puffed up vertically a lot. And if you go looking for a peanut shape or an X shape, there's a very strong X shape in these nearly circular ones, whereas there's no hint of that in the stars that are more elliptical. Now, why is this interesting? Why does this tell us anything about what's going on in the Milky Way? Well, to explain that, stars, when they're first born, they're typically born on nearly circular orbits. But then as time passes, they interact with spirals, or there could be explosions of supernovae, or there could be, more important than explosions of supernovae, there could be gas clouds that go by, and the stars, their orbits get heated and heated. What I mean by that is the orbits become less and less circular. So these would be young stars. These would be old stars. So this is another way of saying that, is that we expect the young stars to have a clear peanut shape and be very thin, but have a very strong bar, and the old stars to be quite thick, have a weaker bar, and not have a strong X shape or peanut shape. The other thing that happens is, if you look at a fixed location within a galaxy, later and later stars, later and later generations of stars get increasingly polluted by supernovae. So the first stars that form will have some metallicity. The next generation of stars that form out of the gas that has been polluted by those stars, by the previous generation of stars, will have more metals because the gas has been polluted. And so increasingly, as you go from old to young, you get increasingly metal rich. So these will be metal poor stars, these will be metal rich stars. And so you can already see, I hope, what's going to be our explanation for these two puzzles that I started out showing you. Here's another simulation where now we include all the gas and star formation and all the complicated physics. For the very oldest stars, we have a relatively weak bar. Younger stars, slightly younger stars, just 4 billion years younger, you have a significantly stronger bar, more elongated bar than that one. And that reminds us of this observation that I showed you as one of the puzzles by Catchpole et al. So that was nice. We can explain something. We're in the explaining things phase of this experiment. If we look from this side, if we look at John, actually this is a cross section. If we look at the oldest stars, we see something that doesn't have much of a peanut shape. But slightly younger stars, there's a very clear X or peanut shape in there. And if we now observe these, like in the Milky Way, remember the metal-rich stars have these two arms, the metal-poor stars have only a single peak. Here's our simulation. The oldest stars, so the metal-poor stars, have a single peak. The metal-rich or younger stars, slightly younger stars, are very clearly bimodal. So what we've done is, using simulations, we've discovered a way in which a bar can automatically separate out different populations based upon how circular the orbits of the stars are. And how circular the orbits are correlate with the ages, and they correlate with the metallicity. So that's why we get all these funny behaviors that depend upon the metallicities of stars. And we've invented a term for this. We call this kinematic fractionation, and we understand what is actually happening with this. And we've continued studying this, but before showing you more, rather than showing you more work that we've done with this mechanism, this needs to be a science. So science needs to be falsifiable. So if you come up with a model, I have to also tell you how you should prove me wrong. And so this is one example of a prediction we made back in 2017. We said if we look at the average ages of stars, ignore the very heavy blue stuff, that's the disk in the foreground that gets in the way. But if we look along here, along the center of the galaxy, we have the oldest stars. And then there is sort of a bracket on this side of bluer stuff, and another weaker bracket of slightly bluer stuff over here. Okay, this bracket is stronger than this bracket over here. Now, using these Myra variable stars, a different group from us, Grady et al., using data from Gaia, they went off and did exactly this measurement earlier this year. And they found that the oldest stars are along the center, like we said, over here. And there's a bracket of young stars over here, and another bracket weaker on the opposite side, of the center. So that's a prediction that we made 3 years ago and has now been confirmed observation. That's great. For somebody like me who spends all their time producing models and trying to understand what's happening, this is a nice confirmation of something that we predicted. That's a confirmation for the Milky Way, but we can also predict things for other galaxies. I told you earlier that the reason why we studied the Milky Way is because it's a bog standard boring galaxy. There's other galaxies that look like that. This is, if we were observing the Milky Way 60 million years ago, we would have seen it like this with an X shape in it. This is NGC 4710. And we were interested in what is the chemistry of a bulge like this. And so we went to the model and made a prediction that the metallicity of the bulge will be very pinched relative to the density. The density is shown in red. The metallicity is the black contours. This is the observations we get for the Very Large Telescope. I showed that to you earlier. The density is this dotted lines, the dashed lines. The metallicity, you see, is very pinched as the solid line. So great, that's a second prediction that we made that has been confirmed. That's really nice. And so now what we're doing a lot in my group is actually predicting things that we should be able to observe in the Milky Way. Let me switch to now talking about the disk, because there's something interesting that happens in the disk as well. The disk, there used to be this view that if a star is born in a particular radius, it stays at that radius indefinitely, forever, which led to the idea of what's called galactic archaeology, that we can go to a region in the Milky Way, we can measure the ages of stars, and based on that, we can recover how stars have been forming at that particular location. So galactic archaeology. What we showed, this is back in 2008 now, this is a little bit of a while ago. It was basically a paradigm shift that if we find a star at a particular radius now, final radius, so that's now, so let's say 8 kiloparsecs, where the sun is, it doesn't mean that the star formed it. It could have formed at a smaller radius and moved outwards. And in particular, there are regions within the galaxy, at the largest radii, where almost none of the stars that we find there now formed there. And in this particular simulation, any star that's beyond this dashed curve almost completely came from smaller radii. So if you think about this as archaeology, this is like archaeology where your strata are all jumbled up. And it breaks the simple idea that we had just 15 years ago of what we're going to be able to do with the Gaia satellite. This is now something that is widely accepted, and I want to show you briefly how this happens. You can see that there are spiral arms over here. What a spiral arm is, it took us decades to really fully understand this, is a density wave, and those density waves, that just means that there's a wave that's propagating through the disk. It's going around. There's an excess density there, and because it's got excess density, it's also got excess gravity. Let's say it pulls stars towards it from the front and from the back. And when it does that, the stars can move around in radius. They can go to larger radii, like these stars over here, or they can even move to smaller radii. So how does this work? Well, the physics of it, get ready for this, is what we call wave-particle interactions. And that might sound very complicated, but all it is just this. This is a wave, he's a particle, and we're seeing a wave-particle interaction. The wave is moving through the water, and the surfer is moving at the same speed as the wave, so he gains lots of energy. He moves with the wave. He doesn't bounce up and down unless he tries to bounce up and down a bit. He just moves forward. And the important thing for him to catch the wave, you might have heard that term, the way you catch the wave is you have to paddle furiously to start moving at the same speed as the wave. And once you start moving at the same speed as the wave, the wave just carries you. You no longer need to paddle. You're getting the energy directly from the wave. That's exactly what these stars are doing. Some of these stars will be moving at the same speed as the spiral wave, and they just gain energy and angular momentum from the wave, and they move around. And here are some examples of that in our simulations. If we look at this star, for example, it's born at some radius, then it catches a wave, it catches a spiral, moves to a different radius, goes around at that radius for a while, and then catches another wave, and it moves to a different radius. And the thing that you will notice is that when it does this, you go from one nearly circular orbit very suddenly to another very circular orbit. And you can cover a large fraction of the size of the galaxy in some of these events. And so this is, quite a remarkable thing that is happening. We didn't know about this until about, let's say, 20 years ago, I think, if I've done that right in my head right now. It's a new thing that has been discovered, and we were showing in this work that it's important for the Milky Way. And let me show you how important it could be. And it's also important for us in the Milky Way, for the solar system. So we're going to look at the distribution of the metallicities of stars. We've already talked about the metallicities of stars. If we look at stars that are at small radii, so close to the center of the galaxy, the distribution of the metallicities will look like this black line over here. You see there's a long tail to low metallicities. If we look at radii, at large radii, so stars that are well beyond the center of the Milky Way, further out than the sun is, their distribution of metallicities looks like this. Now you see that there's a tail, but the tail is towards high metallicities. So what's going on here? So there's a number of things that are changing over here. So this is the inner Milky Way, the outer Milky Way, and this is observations, by the way. And the green here is roughly the radius at which the sun is. The first thing you see is that the average metallicity decreases. So why is that? The average metallicity is decreasing because galaxies form like an onion. They form the center first, and then you get an outer layer, and then another outer layer, and you keep growing to larger and larger radii. So the stars that are close to the center, they've had more time to be polluted by more generations of stars. So they get to reach a higher metallicity than the stars that are forming further out, for which star formation started more recently. So that just explains the reason why there is this change in the average. But what causes this change in the tails? Mathematically, what we call these tails is skewness. And we can measure the skewness in some way. It doesn't matter how we measure it. But this has a tail towards low metallicity. So we call this a negative skew. This has a tail towards high metallicity, the yellow one. So we call that a positive skew. So these are observations in the Milky Way using an experiment called apogee. And here are the data points from apogee. There are these triangles over here. And you see the skewness goes from negative at small radii to positive at large radii. They go from tail towards small values to tail towards high values. Now, when we compare that with our simulations, what do we find? This is the really interesting bit. The colored points are our simulation. And our simulation seems to be tracking what's happening in the Milky Way extremely closely, impressively closely. We have a skewness that goes from negative towards low metallicities to positive towards high metallicities as radius increases. Now, here's the fun bit. We can now take these points, and in the simulation, we don't just have now, like we have in the Milky Way, we have all the history of the simulation because we can actually observe it at all the times. And so we can say how many stars formed at that location, how many stars formed at each one of these locations. And when we measure at each one of these locations how many stars formed there versus how many stars migrated into that region, we have that at small radii, only a small percentage of stars migrated there. And then we have this tail to low metallicity. But as we go to increasingly large radii, let's say the orange point, roughly the solar neighborhood, the fraction of stars that have migrated into the solar neighborhood increases and increases until in the outer, in the last point where we were able to measure in the simulation, more than half the stars, roughly 70% of the stars, 75% maybe, of the stars actually migrated there. In the solar neighborhood, where the sun is now, we estimate that more than 50% of the stars migrated there. So the sun was probably born at a smaller radius. You see, this is where the sun is, the metallicity of the sun. And it's not near the peak where stars are forming now. It's more metal rich than that. So the sun probably formed at a smaller radius, maybe at about 6 or 5 kiloparsecs closer in. So, about, let's say 30% closer in than where we are currently right now. And it's a good thing that we moved outwards, because the further in you are, the more stars are forming. The more stars are forming, the more supernovae there are. And supernovae are dangerous. They can sterilize an entire planet of life. So we're sort of lucky. We're migrants. We're all migrants. We've moved along with our sun away from where things are very violent to regions which are a little bit safer for life on Earth to persist. So that's the subject of radial migration. We were able to disentangle this because we have these exquisite simulations that allow us to actually understand what is going on. I want to tell you a little bit about one more thing very quickly, because I'm running out of time. I'm sorry, I'm really taking my time about this. If we look at galaxies in the early universe, we often find that they have clumps within them. You see them sometimes in galaxies nearby, but mostly we see this sort of behavior in very distant galaxies. This would be roughly about, let's say, 7 billion years ago, but we see this also in galaxies that are 10 or 11 billion years ago. And these typically have a mass of about 100 million times as massive as the sun. Our simulations produce these, and the sort of clumps we get when we observe them, like they would be observed on the Hubble telescope, are very comparable with what's observed with the Hubble telescope. Now, okay, let's talk a little bit about the other element. I told you about metallicity, so the proportion of iron relative to hydrogen, okay? Iron is produced by a type of supernova that is long-lived, what we call supernova type 1a. These take about 1 billion years to explode. And what's happening there is you have two stars orbiting each other. One of the stars starts capturing gas from the other one until it gets so massive that it explodes. So that's how iron is more or less produced. The stars over here, or sorry, the elements over here, alpha over iron, the proportion of elements like oxygen or magnesium, they are produced by a different type of star, by stars that live fast, die young. These are very massive stars. They burn their hydrogen very quickly. And by very quickly here, I mean 1 million years to 10 million years. So about 100 to 1,000 times faster than these guys. And they release a lot of these alpha elements. They release a lot of oxygen. So this is why we track these two elements in our simulation. We track oxygen and we track iron. When we look in the Milky Way, this is again apogee. We see that there's a group of stars up here. We call this the thick disk. There's a group of stars down here. We call these the thin disk. And what we've been suggesting is that the fact that there's these two comes about because our simulations produce this upper thick disk branch because there are these clumps in the simulations. And we see this is the thick disk branch, the upper branch. You see that it does look very thick. The thin disk is significantly thinner. The stars, if this is the density versus height, the stars at large height have lots of oxygen as a fraction of iron, whereas the stars closer down, close to the plane over here, have less oxygen compared to iron. So let me skip that and just tell you about this one thing that we're also studying with apogee, what the oldest stars in the Milky Way are doing. We're finding that they're forming at the same time. This is a combination of using ground-based data for the chemistry and space observations for some of the other things that need to go in there. We're finding that the thin disk and the thick disk in observations are forming at the same time, and we get the same sort of result in the simulations. let me just very quickly then jump to my very last subject to tell you that the Milky Way is not perfectly flat. The Milky Way has a bend at large radius. We call that a warp. Here's another simulation that you can look at. We're looking at warps in simulations like this. One of the things that the warps do is they cause the galaxy to tilt ever so slowly. And we measure an average tilting, or in the simulations, we measure an average tilting rate for the galaxies of about 5 degrees per billion years. Billion, not million. Yeah, before I told you the bar rotates by about 1.5 degrees in a million years. This is 1,000 times slower. Remarkably, the Gaia satellite will be able to measure such a tilt. This is the average that we're finding in the simulations. This is the limit that Gaia can measure. And the other thing we find is that the thick disk in our simulations with warps, some stars form in the warp, and those stars then end up in the thick disk in regions like this. So this is something that we will need to do to disentangle with the Gaia satellite, and this is something that a student of mine is working on. I'm going to end with a slide that I've been telling you a lot about the Milky Way and about simulations and how we try to understand it. We are not the only species on the planet that is interested in the Milky Way. I hope you all had your dinner in the meantime. It turns out that dung beetles are also interested in the Milky Way, and they use the Milky Way to proudly track around on the Serengeti to navigate. They navigate by the light of the Milky Way, and this was actually a paper that was published in Current Biology back in 2013. And I find that quite remarkable that a creature like a dung beetle was also very interested in the Milky Way. So I hope I've given you something to think about. Thank you.
Thank you so much for that, Victor. So obviously normally we would have a round of applause, but I'm sure everyone's clapping at home and enjoyed the talk as much as I did. So we do have some time for questions from the audience now. So just a reminder that you have to type these. To do that, you can type, click the little button. It should be an arrow at the top of your screen, and then a question box should appear for you to type, and then I'll read them out as they come in. So we have had a few questions so far. So the first one is quite near the start of your talk, you showed that the universe was comprised of dark matter and dark energy, as well as the matter that we can see. How do you know those fractions if we don't understand what dark matter and dark energy are?
Right, so that comes back to this thing that I was showing you, that there are basically, when we look, part of what goes into this is not the full story, but part of what goes into it is by looking at this cosmic microwave background, we can see how those peaks are distributed. In other words, what the typical scales are. The typical scale here of 1 degree. If the content of dark matter had been higher, that peak would be shifted lower or higher, depending upon what the fraction of the dark matter is within the universe. I wouldn't be able to tell you whether it would be shifted higher or lower if there was more dark matter, for instance. But I know that the models would predict that this changes and these peaks also change. So it really comes down to effectively what you're doing is you're measuring waves on the last surface that had the full knowledge about what was going on in the universe before things started going their separate ways under the action of gravity. I hope that answers your question. It's not a very straightforward thing to do. It does involve models, and it also involves, to get really reliable measurements, it involves measuring things like the clustering of galaxies, etc. But this is cosmology basically, and it's something that people have been doing for the past 20 years or so. And it's the advent of these very detailed maps of the cosmic microwave background that have allowed us to measure in detail what the universe is comprised of. So now we speak of precision cosmology because of things like this.
Great. Another question was, what exactly is in the bar that you were talking about a lot?
All right, I should have told you that. So here's an example. I'm not talking about the one in the Milky Way. Let's talk about this one because it's a real one. This is stars. So what's happening is, first of all, the bar, you see that you get a sense if you look at this image, this galaxy is rotating in a clockwise sense. You get that sense from the spirals over here. The bar is also rotating in a clockwise sense. And what's happening is there are stars in here. They're going up and down like this along the length of the bar. And as the bar rotates, they rotate along with it. And the way the bar forms is you start out without a bar initially, and then there is something that we call in mechanics an instability. Basically, you can go to a system that has a lower energy by producing a bar. And that's what a bar is. And it happens to a lot of galaxies. Now, some galaxies can be helped into, forming a bar by interacting with other galaxies, but that's not likely to be how the Milky Way's bar formed. The Milky Way's bar formed probably by itself, and it's almost certain that the bar in the Milky Way is quite old.
Great. So a question about how you got the line for measurement. So I think what they were referring to was the graph where you had the 3 different curves for the different metallicities, and I think the x-axis was a distance, and I think they were asking how you got the distance.
How you get the distance? So in this plot, this is actually the apparent brightness of the star. And you need to worry about whether there's dust in the way or along the line of sight or not to dim the star. But you can correct for these things. People have developed techniques where they look at particular types of stars, and also actually in this particular case, what's happening is there are spectroscopic observations. So we have the spectra of the stars. We know what type of star this is. We know how bright it should be intrinsically. So by knowing how bright it should be intrinsically, we can actually get the distances of the stars, and that's essentially all that's going on here. It's not a trivial thing to do. Observationally, there's a fair bit of work involved, but it's spectroscopy. It's taking the light of the stars and spreading it out and looking at, for instance, lines of iron, this element here, to look at what the type of star it is that we're looking at, and then that tells you something about the distance.
Great. Does the black hole at the center of the Milky Way affect the shape of the bulge?
Good question. Short answer, no. The reason for that is the mass of the black hole at the center of the Milky Way is about 4 million solar masses, which is another one of these astronomical numbers. It seems large, but it's actually very, very tiny. The mass of the Milky Way is, you need to add 5 zeros on top of that to get the mass of the Milky Way. It's a very tiny percentage. And we have done studies where we will take a simulation, like the ones I've been showing you here, for instance, and we put a black hole in there, and we ask the question, what effect does that have on the bar? It turns out that for the types of masses that we observe, next to nothing. Now, what it might affect is how much stars can form in the center. If a lot of gas gets into the center, counterintuitively, one of the things that happens is that the gas settles into a disk near the black hole and gets extremely hot, and then you get these jets coming up. I don't have a picture of that to show you, but these jets, this is gas that hasn't yet fallen into the black hole. It's just outside the black hole. These jets are so energetic that they can drive out the gas, and then you can actually, for a while, stop star formation. And we think we actually see some of the effect of these jets in the Milky Way, but the effect of them is not very large.
Great. Do all galaxies rotate in the same direction?
Good question. So a few years ago, there was a study. You might have heard of Galaxy Zoo. Galaxy Zoo asked this question of people. So there were a bunch of volunteers that went off and measured whether the galaxies, the spiral arms were rotated clockwise or anti-clockwise. And they were expecting that the universe is symmetric, so there should be equal numbers. of clockwise versus anti-clockwise. And I should say that this is not something that's published. This is something that was told to me anecdotally. So please take that with a pinch of salt. Anyway, the surprising result was that galaxies preferred one direction over the other. I can't tell you whether it was clockwise or anti-clockwise. And being scientists, they did not believe the result. So they did a simple experiment. They swapped the galaxies around. So what was anti-clockwise became clockwise, and what was clockwise became anti-clockwise. And they asked people to, again, please tell us what the sense of rotation is. And to their surprise, it turned out, or maybe not surprise, it turned out that all galaxies were again rotating in the same sense, even though they flipped galaxies over. So what that told them is there's something in our psychology that prefers things to rotate clockwise versus anti-clockwise. And the evidence, there's no very strong evidence of any breaking in the symmetry. If nothing else, it would imply that we're sitting in a special place if that happened, or in a relatively special place if that happened. So no, they're rotating in both directions equally. Good question.
Someone's asked if you could just go over again the analogy used with the C wave to explain the density waves.
Sure, let's do that. So let me find that. So I don't know if you've ever surfed. If you're surfing, you can't just sit on the water and hope the wave will carry you. That's not how it happens. What you need to do is you need to paddle to catch up with the wave. Once you've caught up with the wave, basically what's happening is you're at the same speed relative to the wave, you're constantly falling, but the wave is also moving forward. So you're constantly falling, but staying in the same place with respect to the wave, but the wave is moving forward. That's what happens in the case of surfing. Now, there's actually another sport. If you're ever interested in trying this, you know, this guy is stealing energy from the wave. The other sport is you can go behind the wave and paddle furiously to keep up with the wave. You constantly have to paddle because the gravity is trying to pull you away. But what you're doing in that case is you're giving the wave energy, which it probably doesn't care about because you don't have that much energy compared to the wave. This is exactly the same thing, that you have a wave and the particle is moving at the same speed. What's happening here is you have a star going around in a circle. So it has some angular velocity, we call it. It has some angular speed. How many degrees per million years, let's say, or per billion years. The spiral is a wave. It's also got an angular speed, and it will be going around once every 300 million years or something. I don't know what, some value. There are different spirals with different speeds. So what needs to happen is that the star and the wave need to be moving at the same speed. And because there's a lot of these spiral waves, if you don't catch this wave, you might catch a different wave at some point in the future. I hope that answers your question.
Someone has said that they think they've read the study with Galaxy Zoo. They think they read it in a psychology journal, so perhaps it is published, but not in an astrophysics journal.
Cool. Thanks for that.
Someone half caught what you said at the start about where the Milky Way got its name from. Could you just repeat?
Oh, I didn't really say. I mean, I guess we get the name from the Greeks. That it looks like a band of milk on the sky. It's worth reading the mythology of it, but it basically was thought of as milk on the sky.
We've had another question about dark matter. I don't know if you have perhaps a direction to point them in to learn more about that, or if you want to answer about how we know about the dark matter.
Well, the main reason we know that dark matter exists is relatively old work now, that when we look at galaxies, the first way we discover that dark matter exists, when we look at galaxies, the light drops very rapidly as you move to larger and larger radii. And so you would expect that the speed at which gas goes around the center would also be dropping. But when we look at galaxies, what we observe is actually that the speed doesn't drop, the speed stays constant. And that tells us that there needs to be some additional material, some additional mass that we don't see. And that's what we call dark matter. The same is true when you look at clusters The clusters are clusters of galaxies. The galaxies are moving very fast relative to each other, much more than the gravity of the individual galaxies. So basically, these two methods, actually the clusters was the first way in which people first determined the dark matter, or that there's something unseen, which is the dark matter.
A question about which of your images were computer simulations, which were artist impressions, and which were actual observations of the sky. I don't know if you want to give a few examples.
Like that says something about our, you know, fidelity to the real universe. I hope. Well, I mean, there's a lot of slides. I can't go through all of them. This is an image of a real galaxy. This is an observation of the same galaxy, now looking at the Metallicities. This is the simulation. Again, simulation over here. This is not a real galaxy, that's a simulation. I showed a lot of simulation images. That's a real galaxy, that's a real galaxy. Simulation, also simulation. And that's the real galaxy that I showed you before. So we do, part of what we do is to actually, you know, in order to be sure that we're studying reasonable things, one of the things that I didn't tell you about is the fidelity of our simulations to real systems. Because if you produce galaxies and they look nothing like real galaxies, well, that's not interesting, right? So part of what we do is we produce images like this, and then we compare them to real galaxies. Do they look like this? This is a simulated galaxy. This is not a real thing. This is why, when I was talking about this, you can look at this from different orientations. You can't do that with a real galaxy because you can't, you know, turn around the real galaxies. They're just too far away, obviously.
Great. So you showed that galaxies are these kind of blob shapes or spirals. Why do they just have those two shapes? Why is there not other strange shapes going on?
Right. Well, I mean, there are what we call irregular galaxies. Irregular galaxies. This is Hubble's classification scheme. We've added a few things. There's irregular galaxies. There are S0s now. We recognize there's unbarred S0s and barred S0s. There's dwarfs. There's a whole zoology of dwarfs. There's central galaxies. But bottom line, for sort of most big galaxies, this is a reasonable classification. Whether you form a bar or not, that's still not fully understood, whether you do or not. Why are there galaxies, about 1/3 of galaxies, that don't form these bars? Simulations seem to really want to form bars all the time. So I'm just going to say I don't know the answer to that one because it's an open question, although we have ideas about what might be going on. The reason why there are elliptical galaxies, which have lots of random motion, versus things that are rotating, the rotation comes about because the gas has to cool a lot from within the dark matter halo by a factor of 10. And so if it's spinning very slightly when it's on a large scale, by the time it cools to very small scale, it's spinning very rapidly and you get a disk. And that's also true in the solar system. You start with a pre-solar cloud, it cools, it collapses a lot, and you get a disk. That's why disks form in nature, and they're very common in astrophysics. These guys, the way these guys probably form is that you get two of these galaxies or more of these galaxies, they merge into each other, and then you end up with one of these blobs. This is the fate of the Milky Way. The Milky Way, in I think about 4 billion years time, will merge with the Andromeda galaxy. And at the end of that, we'll end up with, whoops, let me just show you that very quickly. So this is the Milky Way. We're in the Milky Way, so it's nearby. That's the Andromeda galaxy. These two galaxies are going to merge in a few billion years, and then we will end up on one of these elliptical galaxies. I hope that answered the question. Clearly, there's a lot that goes into this. It's been decades that people have been working on understanding this.
So at the end, you showed the warp of the Milky Way. Why does that happen?
Right, I was going a little bit fast at that point. I'm sorry. I was very conscious of the fact that I was running out of time. So very quickly, let me remind you, there's this filamentary structure. So this filamentary structure funnels gas into the dark matter halo and then it will cool and settle into the disk, or a galaxy like the Milky Way. When that gas comes in, it's got a spin that's different from that of the galaxy at the very center. So as a result, when that gas cools, it will cool with an axis that is very different from that of the main galaxy here. Now that's one way in which you can do that. I mean, this is not fully settled in the simulations. We definitely see this as a important mechanism. Another mechanism is that you could have a satellite go by and you could tilt up the galaxy, the outer part of the galaxy. But what we're seeing predominantly in our simulations is that it's actually gas that comes in with a different spin from what the stars have. I hope that answered that.
Do your simulations or any other thing that you know tell you how many black holes there would be in the Milky Way?
Right. So if we ignore, I'm going to assume you don't mean the central black hole. If we ignore the central black hole, which there's only one, there might be more sort of like it, intermediate mass black holes, we call those. If you're asking me how many stellar mass black holes there are, so stellar mass black holes, some of these supernovae, when they explode, what they leave behind will be black holes. And so how many black holes are there in the Milky Way? There will be roughly a comparable number of black holes as there have been stars of that mass, which I don't know what the number exactly is, but let's say, roughly speaking, if you're a star and you start out with, I don't know, I'm going to guess a little bit here, 50 solar masses, 50 times as massive as the sun, then you end up as a black hole. And the question then you can say, given that we think that the distribution of masses of stars is roughly constant, it's not quite, or people think it might not be quite, but if we think that it's roughly constant, we can predict how many black holes of solar mass or solar mass-ish there are at the moment. I don't know that number though. It would be on the order of millions, but I don't know what the number is. Millions or billions, actually.
A question that says, how heavy is the universe? I don't know if you can answer that.
I don't know if I can answer that. What I can tell you, I don't know how heavy the universe is. I don't know if there is an answer to that. What I can tell you is not how heavy it is, but how dense is it, which is the really important thing from the cosmology point of view. There are three limits you can think of. The universe could be so dense that gravity eventually fails to keep the universe from continuing to expand, and gravity eventually not fails. Gravity eventually wins over and collapses everything back. And that we call that, we refer to that as a universe which is closed. The opposite extreme is that you could have a universe in which the gravity, there's so little mass in the universe that the gravity is so weak that the universe just basically expands forever. And then you can think of the limiting case where the universe expands increasingly slowly, but never quite collapses and never quite takes off. And we seem to be living in that, in what we call a flat universe. And there are some units in which that special density is 1. And we're living in a density, we're living in a universe with a density very close to 1.
Does space-time affect the observations of galaxies? I assume they mean kind of warping and things like that.
Well, so I'm assuming you mean something like gravitational waves and the change of space-time. Those sorts of effects, what we call general relativistic effects, become very important on galactic scales when you're close to the black hole, which is a very small scale. So things like the warp are not affected by gravitational waves or the things like that. Now, there are exotic theories like cosmic strings, and maybe cosmic strings would have an effect on the Milky Way if we were next to one. I'm not aware of being close to one. I'm not aware of anybody having discovered these things.
Someone asking if you could just recap where the iron comes from in the stars
Sure.
that you're looking at.
The iron comes from stars, from a special kind of supernova. So you have two stars orbiting each other. So one of the stars will have been relatively massive. It will have consumed all its hydrogen, will have turned it, when I say consumed it, what it means is it's turned most of its hydrogen into iron. You cannot make elements heavier than that in sort of ordinary reactions because you need to put in energy rather than you get energy out. So stars cannot do that. So it will be a star that has a very massive iron core, and then it's just sitting there slowly cooling down perhaps. But if there's another star around it, then gas can fall into the sort of dead star, let's call it. If you build up enough mass, eventually the star cannot hold up against the additional gravitational forces, and it just collapses. And that collapse is a supernova, and that releases a lot of iron into the gas. Yeah.
Right, we've come to the end of the questions, and we're just coming up to 9 o'clock as well. So I think that's an appropriate place to end. Thank you so much, Victor, for answering all those questions and for your talk in general. It was really informative. And yeah, it was great to look at so many pictures of the Milky Way and understand our place in it.
Thank you.
Thank you everyone for joining us as well, and we'll be back in 3 weeks' time and on a talk on topology. So again, don't forget to register same way you registered for this one online, and if you want to join our Facebook group, you will be able to kind of get reminders about joining us as well. So just search for Birmingham IOP lectures to join us there. Great, thank you so much, and we hope to see you soon. Bye.
Bye-bye.